So welcome to OneQuantum Nepal. I'm the president of OneQuantum Nepal. I see some new faces, and maybe I want to start by telling what we are doing here, right? With OneQuantum. OneQuantum is an initiative. It's a non-profit initiative, and the main idea with this initiative is to sort of like have this quantum technology, right, or make this quantum technology inclusive for people from all walks of life, no matter where they come from, what the background. And we want to give sort of platform, right, for people to learn this technology and be familiar with it, and participate, right, in this so-called second quantum revolution. And we have a lot of projects and programs under OneQuantum. We have different chapters, right, representing Africa, South America, Nepal. We are like few dozens of chapters right now, and each of these chapter focuses on different country, and we build community, quantum community locally, right, and we provide mentorship programs where we match you guys with mentors, right, from different quantum fields, from people working in companies, academics, right, who are knowledgeable in quantum technologies. And we welcome you guys to participate, right, in this mentoring program. I'll send a link a little bit later about that. And of course, we also have project. We successfully completed one project about Grover's algorithm, and you guys participated. It was led by Abhiskar and Manish Pai, and we have successfully completed Grover's executing Grover circuit on a real quantum computer, right? And we tested how it performs, a simulator versus a real quantum computer, right? And we got a pretty good result for that. So they will have more projects in the future, right? We were looking at optimizing project, and I welcome you guys to really participate in this project. And of course, we have speakers, like Miha, who is an expert in what he does. I will bring experts, like him in the coming future. This is the last talk in the series Summer of Quantum, and we will also launch summer, quantum application, right, like in the next few weeks, where we bring speakers, who understand use cases, right, in quantum. So we will have another series of speakers. So without further ado, I want to introduce Miha. It's pretty special this time because Miha, he's my colleague. We work like together at IQM Quantum Computers. He joined IQM a couple of months ago. I think 9 months ago. Is it correct, Miha?
Yeah, I started like 15th of January officially.
Yeah. He started 15th of January, and he comes from Slovenia. He comes from the capital of Slovenia, and the capital of Slovenia is called Ljubljana. I've been there twice. It's a beautiful small city. He's very into sports. He does marathon, climbing. He's a little bit of sports freak, and he has formal training in physics. Of course, he completed his master's in physics from Ludwig Maximilian University, LMU, in Munich, which is a reputed university in Germany. And he works right now as a quantum engineer to build a future of quantum computing from IQM, and he's based in Germany. So without wasting any more time, I would like to give the floor to Miha. And of course, thanks, Miha, for doing this. We are all very excited to hear what you have to tell us about noise and how it relates to quantum physics, right? Thanks, Miha. So yeah, sure. Go ahead.
Yeah, thanks for the very nice introduction. So yeah, I guess I'm just gonna, but yeah, you need to let me share my screen. But yeah, maybe just like as an introduction, the point of like today's lecture was to try to give you an idea of why we haven't built a 1 million qubit quantum computer yet. So we're going to talk about like noise in quantum circuits, like try to give you a physical intuition of where this comes from, and basically why it's also that big of an issue here. But yeah, sure. Yeah. Okay, so yeah, I'm not gonna say anything more about myself. I think Manish more or less covered everything. So yeah, maybe let's start. So this is like kind of what I wanted to talk about today. Like, first of all, like what even is noise? Like how do you define that like in very, very rigorous physical sense? Like what does it actually mean? And then like maybe look at an example of how we usually deal with noise in physics. So for this example, I chose like a classical one, not a quantum one, just like to keep things like a bit more simpler. And then I want to delve into this like quantum world of like weird stuff, and then how and try to connect all of this. So after like going through this like lecture, I did realize that it might be a bit high level. So if anybody has any questions or any other consideration, they can always like ask a question in the middle. We can discuss a bit. Like I said, hopefully it's I'm gonna be try to be as clear as possible, but like if something is weird, if you don't believe me, then you can then just like raise your hand or just speak up. So yeah, now let's really start. So yeah, what's noise? So most people, when you mention the word noise, is they're gonna think about something like this. So like a huge noisy road, whatever. You're trying to talk to a friend, you can't hear them. There's like a lot of noise in the background. You're trying to work. There's like noise in the background. This is what we like usually imagine as noise. But noise can be like a lot of different things also, right? So I mean, I don't know how old you guys are, but I still remember these like old cathode ray TVs, where if you didn't like have the correct frequency, if you didn't catch the signal, you would just like see something like this. So this is what people would call like white noise then, if you've seen it. And then if anybody here is like a bit more experienced in electronics, you know that like also in electronics, sometimes you try to measure a signal. And because there's some noise somewhere, what you're gonna see is not this like nice, well-defined shape, you're gonna see some fuzziness around it, right? But then also the interesting thing is that like for us in Slovenian, we have different words for like noise on the street and noise, for example, the one in the electronics or on the TV that I showed you. I'm not sure how it is in Nepalese, but like in English, all of this is like considered to be noise. But then, yeah, you have to think about like what's the connection between this kind of noisy road and this like, you know, random thing that you measure, I don't know, in the lab. But basically what we normally call noise is due to a signal. Basically, noise is basically a manifestation of the fact that our system, whatever we're observing, is usually not completely independent. You always have like some kind of environment, and then you have like a system which is part of that environment, and you have some interactions between your system and the environment. And now to be like a bit less abstract here, so this system can be, for example, like in the road example we saw earlier, the system that you're trying to measure or like interact with would be maybe your friend like trying to tell you something, and the environment is, you know, all the cars on the road. And these cars on the road, they also like, you know, they also produce, you know, their own sounds, which are gonna basically mess with whatever you're trying to hear when you're talking to your friend. So then if you look at like maybe another system like that, like old school TV or basically any kind of electronics component, so your TV or your antenna is never going to receive like one frequency, one signal, like the TV channel that you're trying to watch. It's always going to pick up other like electromagnetic frequencies, like for example, background radiation, for example, from space is also like one of the contributors to that like white fuzziness you saw on a cathode ray TV. And basically, why we see this randomness is usually because we have this like huge environment where like a lot of things are happening at the same time. And because it's just like hard to describe every single part of the environment, we just like see something random and messy at the end of the day. And it's like the same thing kind of holds for a qubit. So I'm not really going to go into like the details what a qubit is here, but since you've most likely had some quantum lectures before, you know that it's just like it's a physical system, a quantum system, which has a 0 state and a 1 state. And like every single thing in this world and universe, a qubit is never perfectly isolated. So also a qubit has some kind of environment, and that environment is gonna like affect how that qubit behaves. And what I want to like kind of try to tell you about today is like how this environment affects the qubit. But what I really want to like stress out here is the fact that like noise in its essence usually originates from like this huge environment, which is somehow coupled to whatever you're trying to like analyze in your physics. And now for the next step, I thought that, okay, maybe it would be nice if we did some actual physics. So I decided to look at this like example of basically a classical example of so-called Brownian motion. So Brownian motion is this like a pretty old like mystery in physics. I mean, it hasn't been a mystery for 100 years, but like it's Mr. Brown, the guy who discovered this, was a botanist, and he was basically observing pollen grains like floating in water. So for example, your system here, like going back to the previous picture, would be your pollen grain, and you want to know how it moves, and your environment, the huge environment, which is like interacting with it, is the water molecules in the solution, right? And this is like this is how these pollen grains move was just kind of a mystery for, some time, until like this guy, Albert Einstein, came up with this like solution that I'm going to try to like explain here briefly. And basically the idea here is to try to predict how these like pollen grains move. And what we're going to do here is just like write a simple physical model. Like we're going to do some actual physics, and we're just going to imagine this like pollen grain as this like huge yellow sphere, the thing that's like displayed in this animation, which is like in this box full of these small, very, very fast balls, which are water molecules. And this is basically pretty close to reality. So like I said, this is like a classical example. Yeah, sure, I see a hand raised. You can go ahead if you have a question.
Yeah, go ahead, guys. Somebody had a hand raised? Or was it accident? Maybe it was an accident. Never mind. Yeah. So if you have questions, just raise your hand, or you can also write on the chat, and I can submit to Miha at the end. Yeah, go ahead, Miha.
Yeah, okay. So let's start. So we're going to treat this problem like you would treat any other problem in your high school physics class, right? We're going to start by writing down like Newton's second law. So force is equal to mass times acceleration. And then, so the next step would be then to identify the forces acting on our pollen grain. And this is basically, okay, so I'm not sure if you guys are aware of this, but you know that like if you have a object moving in a liquid, the faster that object moves, the more like drag it's going to experience because of this viscosity of the liquid. So you know that, for example, it's like way harder to swim in honey than it is to swim in water, just because honey is way more viscous. And we know that this force is going to slow you down the faster you go. So we're going to write like in our Newton's law, this minus k times v, where k is a constant and v is the velocity of our particle. And then to that, we're going to add this random force, which is going to be the effect of our environment. And why we're going to do this is, I mean, you might say, okay, but the random force comes from the water molecules, and the viscosity obviously comes from the water molecules. Why do we even have to separate them? But if you think about it, at like zero temperature, all of the water molecules would be completely still. Actually, they would be frozen, but we're just gonna like assume here that we have like a water which never freezes. And even if all these water molecules are still like not moving, as this pollen grain will move for like this unmoving water, it's still going to experience drag, while it's not going to experience any like random collisions with these water molecules. So that's why we need to like kind of separate this effect of this random collisions, which are described by this eta function here, and the viscosity. And this is basically everything that you need to know to solve Brownian motion. This is what Albert Einstein did, and this is like basically his solution. The next step would be to solve this equation, which is actually somewhat non-trivial, but if you ever go into like a STEM degree in university, you're going to learn how to solve these types of equations relatively quickly. But what we need to like really, I see another hand raised, so maybe there's a question this time. Let's see.
Yeah, Siddharth, do you have a question?
Yeah, I mean, if not, we can also like discuss this stuff at the end.
You can also write on the chat if you have a question.
Yeah, so the chat I'm probably not going to be able to look at, but yeah, please warn me if there's something there.
Yeah, sure.
So yeah, the next thing would be to kind of what are the properties of this like random function? What are the properties of this like huge environment acting on our pollen grain? So the thing is that like everything here is random, right? We never know like which water molecule is going to bump into the pollen grain at what point in time. So we can only say like on average what's going to happen. And we know that like the probability of a water molecule like bumping into our big pollen grain from the left is the same as the probability of it bumping in from the right, because why would it be any different, right? So that's why we're gonna have this like first condition that the average of this like random force is 0, because the left and the right bumps, they should cancel out always. And then the other thing is that we're gonna assume that basically if you have a collision at one point in time, then it's not necessarily that you're going to have another collision. Ooh, well, what's that? Yeah, sorry for this green line. I don't know what happened here. Is that you're going to have a collision in another point of time. And this is like this is a bit cryptic now. I know it's probably kind of hard for you to understand, but this is like what this average value denoted by these like rectangular brackets is going to tell you. Basically the fact that like if you have a collision at one time, it's not necessary that it's probably very unlikely that you're gonna have like another collision later. Okay, this is sorry about this, guys. No idea what's happening here. Oh, now it's everywhere. Jesus Christ.
Yeah, is there like some button being pressed? Do you have external keyboard or?
No, I'm having like a Siddhartha sign. I don't know why. Okay, I'm just gonna stop my screen share for a second and then I'm gonna come back. Sorry for this.
These in the chat, boys. Sorry, what's that?
Yeah, I think, yeah, no way we're gonna just like
maybe
start.
I think somebody accidentally is drawing something. Please don't do that if it is by accident. Yeah, go ahead. Maybe try sharing it again.
Oh yeah, you need to enable me to do it.
Yeah, okay.
Okay, here we go now. Yeah, here we were. Okay, yeah, so sorry. We just want to solve this equation, right? We have some kind of random force which describes our collision, which has some properties, and then it looks something like this. So it's completely random. You never know when a particle is gonna hit and which direction you're gonna push the big pollen grain. Now, okay, so to cut this like whole thing short, I'm just gonna like show you the solution to this. And the thing is that like we can only give like nice solutions in terms of like average quantities. We know that what's going to happen to this like big pollen grain on average, but like trying to predict each individual like path of each individual pollen is like kind of hard. But we can say that like if it starts out, oh, here it is again.
Yeah, I don't know what's happening. Wait.
Yeah, I think if we suspend the participant activities, then I think no one will be able to annotate the screen.
Yeah, okay. Okay, let me check.
Let me do this. Now, can we make host to Miha Papic so that it will be good?
Yeah. Yes, so I gave host to Miha and co-host to you. And one of the participants' activities have been suspended. I hope this is by accident. And please don't annotate it because it's annoying for the speaker, Miha, who has given his time to, tell us about this stuff.
I know that like maybe this last example isn't the most interesting thing in the world, but there are like some points that I want to like kind of come across here. But we just know, like I said, the only thing you have to remember here, like even if you forget all of these like physical stuff at the beginning, is that like on average this pollen grain isn't going to move because the probability of like a particle bumping into it from the right and the left is the same. But that's because they cancel out, right? You have a plus and a minus sign. What if you looked at the squared, so kind of the distance traveled of this particle, and that's going to increase with time, and it's going to increase like according to this formula. So the coordinate like x squared on average is going to increase with time. So this is just like the solution of this like pretty nasty looking equation with this random term. But then what I want to really kind of incentivize you to think about is like a couple of details, like what happens if we have a higher temperature and a lower temperature. And also did we treat this like problem like completely? Are there any forces that we're missing here? So this is just something you can think about in the background. But what I wanted to maybe like elaborate more is on how exactly this motion looks like. So I gave you like some equations, which is pretty abstract. I want to like now show you like, some examples of this polling grain actually moving. So we're just like assuming that in the beginning it's 0.0, and then like at low temperature, all of these random collisions, they're going to be, the molecules are going to be pretty slow. So they're not going to like change the position of this big polling grain by very much. And it's just going to kind of randomly like go somewhere. But at higher temperature, basically these water molecules are going to move even faster. So if a fast water molecule bumps into this big polling grain, it's going to push it even more towards one direction. And what's going to happen is that like this polling grain is kind of randomly going to move, and it's going to move faster. So this is basically what the solution of this equation tells you. And this is just like two examples of like a trajectory. This is what we would call a trajectory, like two examples of like a motion. But if we look at another polling grain, it's going to move a bit differently. So it might go like this, like see, there are two other trajectories here. So time is increasing like in the downward direction here, and then like the position is like on this x-axis here. And you can see that like on average, if you would sum these two up, they would be pretty close to zero always. And also like in this case. And this is basically what the solution of this equation tells us. But what I want you to remember from this example kind of is that like more temperature means more randomness, and more randomness means way harder, less deterministic movement of the polling grain. Because at higher temperatures, it's really harder to tell where this polling grain is going to be at an arbitrary point of time than at lower temperatures. Because at lower temperatures, we're always going to know that it's going to be closer to zero than at higher temperatures. So this is why this idea of like temperature is kind of a measure of randomness, where it kind of comes from, like illustrated on an example. Okay. So yeah. Now let's go into the quantum stuff. So we have this like quantum example. So we have the classical example, which I would kind of try to ask you to kind of remember a bit. But like I said, the only thing is that try to remember this picture of like one polling grain, one system embedded in this like huge environment of a lot of small water molecules. Now let's go into quantum mechanics. And we're going to start with just like, the basic example of quantum mechanics, Schrodinger's cat. So Schrodinger's cat is, I mean, you've probably seen it before, but I'm just going to go over it to be a bit clearer. And it's basically, we have a cat, which is in like a quantum superposition. So in this like weird state, which is described by this like superposition of cat alive plus cat dead. But then when we look at the cat is either alive or either dead. It's not both at the same time anymore. So we change the cat just by looking at it. And this is like kind of how quantum measurement works, right? It's weird because if you look at your cat, you're going to change the cat. This doesn't happen when you look at, I don't know, a table or a chair. If you look at a chair, it's still going to stay a chair. But if you look at Schrodinger's cat, you're going to change the cat. And then maybe let's formalize this a bit more. So in terms of actual like quantum mechanical stuff. One more point. So Schrodinger's cat is basically the same thing as a qubit, right? A qubit is either 0 or 1, or it can be any quantum superposition. And the cat is either alive or dead, or in this like superposition. It can be anything. So in the remainder, I'm always going to use this cat example, but you could always replace alive and dead with a 0 and a 1, and you would see the same thing happening with a qubit. But basically what I wanted to say is that like, if you measure this correspondence between like classical and quantum stuff. So the quantum world is weird. It behaves completely differently from what we're actually like used to. And there are like, certain similarities with like classical physics, but at the end of the day, we're just like too big to understand quantum mechanics. Like electrons are way too small for us. And it's like kind of, why would you expect like an electron to behave in the same way as, for example, your table? So they have different laws that they obey. And this is what I want to kind of trying to show you how this works a bit more. And I'm not going to prove anything here. the thing is that like this is something that you have to accept. It's weird. Nobody likes it. Nobody understands it very well. But it's the thing that currently works pretty well. But so in quantum mechanics, what happens is like if you look at a system, you change it. And basically what happens is that if you're looking at a system, what that actually means that you're measuring something. You're measuring, for example, the energy. And if you're measuring the energy is described in quantum mechanics by what we would call an operator. This is a very weird word, like an operator, but basically an energy has like its own specific functions, wave functions, like alive and dead, but an energy has like an energy 0 function and an energy 1 function, and energy 2 function, stuff like that. And as an example of these like functions, I have this like have them like illustrated here on a basically 1D example of this like small ball. So this is the classical version of this, which is kind of trapped between two walls, and it can only move in one dimension, left or right. So classically, what happens on like figure A is that it just like randomly, no randomness here. It's just like jumps from left to right and bumps, and it's going to bump like that up to infinity. But a quantum ball is going to be very, very different. Like I said, it's no longer described by like a set of coordinates, but it's described by a wave function. These are like some examples of wave function in this system. And you might be like pretty familiar with these if you've ever seen like a string. And if you look at the frequencies of a string, like how it oscillates. And this is like the same thing, literally the same thing. So you can see that like they all kind of oscillate, they change in time, but these are what you would call energy eigenfunctions. And this is again something that you don't really have to remember, but what you have to note is that if your system is in one of these like special functions, you're gonna measure basically, okay, sorry. So you have these special functions, which are B, C, and D. And then you can also have your system, which is in a superposition of these special functions, right? Which is, for example, E and F. You can see that E and F are something pretty weird. But if you measure E or F, after your measurement, your system is going to be either in B, C, or D. So again, you're changing the wave function into one of these like special wave functions, which are determined by what you're actually looking at here. And okay, yeah, I think now that I'm confusing you maybe a bit too much, but let's just go over this like once again slowly. This is basically how how quantum mechanics works. So you have a quantum state, and then quantum state like evolves with some kind of equation which you solve in any way possible. And then you measure the quantum state. And the measurement result on a quantum state is going to be random. So if the cat is like reading this like alive and dead at the same time, you never know when you look at the cat whether it's going to be alive or dead. This is always going to be random. But afterwards, after the measurement, if you see that your cat is alive, your cat is going to stay alive, even if you look at it, like a lot of times, like way later. But the thing is that like after you've looked at the cat once, it's going to stay alive and it's going to stay dead. So if you actually want to make a measurement, you have to learn about what the cat looked like from the beginning. You have to look at it many times. Because if you see that, okay, 50% of the time the cat is alive, the 50% of the time the cat is dead. But if you only look at the cat once, you're going to see alive or dead. But this is like this kind of issue of quantum mechanics where you actually have to measure everything a lot of times if you want to actually learn something about the system. And here, for example, like this randomness does not like exist because of some kind of huge environment. This is a randomness which is always there. And it's like we just have to, like I said, deal with it. You can't prove this. It's just the way that it is. But what you have to again, remember from this slide is kind of that after you measure a quantum system, in general, you won't be able to know what your single measurement outcome is going to be. But if you know the wave function, you can kind of guess with a certain probability what you're probably going to measure. Unless if you know that the cat is already alive, then you know that it's always going to be alive. But if it's in a quantum superposition, then you never know what's going to come out of the box or what's in the box, whatever. And this is the origin of this randomness is pretty different from the one in Brownian motion, where you have this huge environment, right? So yeah, these are like kind of the basics of quantum mechanics, and they're weird. You have to kind of personally deal with them. But once you start working with this, once you come to accept this, then you just accept it. But like I said, there is no way to prove this. Like realities sometimes can be kind of weird, it can be unintuitive, but the issue is that we're really kind of too big to understand quantum mechanics. But we can make, very good predictions. If you're a physicist, you can like say a lot of things about your Schrodinger's cat, right? It's going to be either alive or either dead, and depending on the wave function, you can like tell the probability of it being alive or dead. But that's as far as we can go. We can only talk about probabilities and what we're most likely going to measure, but we never know what we're actually going to measure when we look at the single measurement. And now, okay, let's finally get now to the qubit. So what I have here is just like a picture of a QPU, a quantum processing unit of a quantum computer. This one I think is from IBM. It's not from IQM. Sorry, I didn't find like a picture in our folder. And what you see here are what I highlighted with these like red circles are 4 qubits. And these qubits are quantum objects. So they're going to have this like randomness because of their quantum, like the Schrodinger's cat is going to be either alive or either dead. They have this like inherent measurement randomness. But you can always also see that there's like a lot of stuff going on here. So you don't see just qubits, you see like these weird wiggly lines and a lot of stuff going on here, which honestly, even I'm sometimes not sure what exactly I'm looking at here. But the point of this picture is that this qubit isn't, again, isolated perfectly from the environment. So a qubit has 2 sources of kind of randomness affecting it. And one is this like measurement randomness from quantum mechanics, and the other one would be this environment from Brownian motion. And now we just have to kind of consolidate these 2, right? What they actually look like. And yeah, maybe also like, as another like throwback to the Brownian motion example, like these qubits are always like cooled to a very, very low temperature. And one of the reasons, I mean, there are also other very, very important reasons to do this, but one of the reasons is also that your system is less noisy, just like in Brownian motion. Lower temperature means less noise. And now we can maybe actually go to a actual like quantum computing example. Okay. So again, like recapping Schrodinger's cat. So quantum superposition, which you measure, and then you don't know either it's going to be dead or alive. But after the measurement, it's always going to be dead or it's always going to be alive, depending on what you measure. But what is an actual measurement here? It doesn't necessarily mean that somebody has like, looked at the cat. It doesn't mean that a human has to look at the cat. A measurement can be anything. For example, if like a small grain of dust ends up on your qubit, it falls there. I don't know, you have some dust in your room, that happens, right? That's basically the same thing as a measurement at the end of the day. Somebody has nudged the quantum system. Somebody has opened the box of the Schrodinger's cat. And this is obviously then going to affect your qubit, right? We know that like after you look at Schrodinger's cat, it's going to be either alive or either dead. And this is very different from the Schrodinger's cat being in a superposition. So this grain of dust is changing your qubit, right? And it's changing it from a quantum superposition to this like either dead or either alive, which is, so it's either 0 and 1 at the same time, or it's either 0 or either 1. But if it's only 0 or 1, if these are the only 2 possibilities after the measurement, that's just a classical bit. There is no quantum advantage here. Then you're basically building like a very, very expensive laptop with 12 bits, which is completely useless if you have like these grains of dust or any other like unwanted effects from the environment playing around with your qubit. And this is like what people then like to call decoherence. So the fact that like you have a qubit, and then something happens to this qubit, something from like the outside, it can be dust. For example, dust is like an example which you can imagine pretty easily. But protecting the qubit against dust is pretty easy. You just, you need a very, very clean room without any dust, and that's it. But there are other, unwanted things like electromagnetic radiation from, for example, also subways, stuff like that. They're also going to have the same effect. But the fact that this dust grain destroys your qubit and turns it into a bit is like a huge problem, right? And it's also going to completely destroy your kind of quantum population. And people call this decoherence. This is like a very professional word. But basically what it means is what I described, that something happens to a qubit and it collapses it into one of these like states, into either cat is dead or cat is alive, or qubit is 0 or qubit is 1. But this kind of decoherence process is something that kind of, if you can only say that like a grain of dust is going to end up on my qubit with a 99% probability in this time, stuff like that. So it's kind of a continuous process. After 1 nanosecond, maybe there's going to be no dust on your qubit, but after like 1 hour, maybe 1 grain of dust is going to end up there. But what that means is like the longer you wait, the higher the probability of your qubit actually decaying from a qubit into a classical bit is. And this is, again, like I said, due to this like picture of noise originating from a huge environment which interacts with the qubit. But the only kind of caveat here with qubits is that, yeah, we would want to make them, as isolated from this environment. So to make them like more as quantum as possible so that they don't collapse into like cat is dead or cat is alive states. But the issue is then going to be that if our qubit is very, very much isolated from an environment or from basically the whole world, how are we going to do operations on it? Because in quantum computation, you have to change the qubits, right? To actually get like a quantum program. And furthermore, you have to measure whatever your quantum computer has produced. And if you want to measure the qubit, you have to interact with the qubit. And if your qubit is isolated, you can't interact with the qubit. So you have this very, very fine line of if you have a qubit which you can measure and control very well, it's also going to have more decoherence. So it's going to collapse into a classical bit more with a high probability and quicker. But if you have a very, very, very well isolated qubit where you can do like long, computations, the issue is going to be like, how do you actually control these kind of qubits and how do you measure them? And currently, like, for example, all the big guys like Google, IBM, they have been building qubits which have a lot of decoherence, but they're also easy to control and measure. So this is like the path that people have been going on to. But the reason basically why we don't have like 1 million qubits at the same time is because they're just going to decohere too quickly. This is like one of the main reasons why we don't have quantum computing yet, because we don't know how to isolate a qubit from its environment, from this like random stuff well enough. But people have been like working on this like very, very hard. So I have here like maybe, a lot of fancy words. But what you see here on the y-axis is kind of the lifetime of your qubit. So how long your qubit is going to stay quantum before it collapses into cat alive or cat is dead. And you can see that like in the past years, this has gone from, like nanoseconds to basically microseconds. And if you would, and this is also a pretty old plot. Right now, the current record for the longest living qubit, I think, is around 1 millisecond already. And, like 20 years ago, it was 1 nanosecond. So this is like really, so quantum computation is looking very, very, it's looking good for now, but let's see how it evolves in the future. And yeah, this is basically how I want to conclude my lecture. Hopefully I didn't confuse you guys too much. I was rambling about a lot of like seemingly non-connected stuff, but hopefully if you think about it a bit more, it's all gonna make sense. But yeah, these are like kind of the main takeaways I was hoping you would like get from this lecture. So the fact that you have that noise usually means like a very, very large environment, which is so big that it looks random, just because you have so many, many small particles, so many like water molecules in your like, glass of pollen particles. And this like, these small random motions of these like water molecules are going to manifest themselves as kind of random fluctuations in physical quantities, like the force or the energy acting on your pollen particle. And you can kind of measure like how random your system is with the temperature. And then like going to the quantum case, then I was just like hoping to give you like an intuition of like what is decoherence when you see this like big fancy word somewhere that okay, decoherence means that like our qubits has become useless because something has interacted with it in a negative way, in an uncontrolled way. And like I said, decoherence currently is one of the most, I think, pressing issues in quantum computing. There are obviously also other problems that we have to deal with. But like I said, that's also what I've been working on here at IQM a lot, also during my master thesis. And I also think it's kind of, just interesting to see how like something which is random, which you would think that you have no idea of how you're going to actually predict anything with something which is random, how you actually are able to make some kind of physical predictions at the end. And yeah, thanks for the attention. And like I said, any questions, clarifications, like please feel free to ask. I have a feeling that this was like a very like high level lecture if you're in high school or, but yeah, sometimes when people talk about the things that they're interested in, we like to go overboard.
Okay, thanks for letting me speak. Okay, I have a question. You have mentioned that electromagnetic waves also disturb the quantum superposition.
Yeah.
Then does only magnetic field also disturbs quantum superposition, or?
Yeah, if you have a random magnet, yeah, it also magnetic field is going to affect.
Random magnetic fields, or does the magnetic field of Earth also affects it?
Luckily, the magnetic field of the Earth is small enough, it's weak enough for it to not have a very big effect on the qubit, and it's also pretty constant, right? The thing is that it's not something that randomly appears on the qubit. It's always there. So that's also one benefit of the magnetic field. But the main thing is that it's like very, very weak. But for example, the issue is like more or less electromagnetic radiation, which has a higher frequency or energy. And these can be like, for example, like cosmic particles from space bumping into your qubit. This is like an issue, for example.
Thank you.
All right. Can you hear me, guys?
Yeah.
Yeah. Okay. Miha, can you give me back my host privilege?
Sure.
Host. Yeah.
Just gonna stop sharing my screen.
Yeah.
Then
yeah, you can just click on my screen and then there should be.
Just a second.
One slide. Yeah.
Yeah. Okay. Yeah. All right. So any more questions for Miha? Sorry, Aviskar, what were you saying?
If Miha wants to share screen again, then you can make host to him, so he will be able to share the screen.
Yeah. Yeah.
Yeah.
All right. So okay, so there is a hand raised from Susan Sapkota. Is it by accident or did you have a question, Susan?
Actually, I see some questions in the chat. So the first one is the quantum processor that I'm referring, is that a quantum chip? So yeah, that is the same thing. Yeah, sorry for, sometimes I use these big words from, working in the field, which are most of the time completely unnecessary, but they are kind of ingrained in my brain, and it's sometimes every now and then they slip. But yeah, a quantum processor is usually the same thing as a quantum chip. It's like a small piece of some kind of material where you have like a qubit printed out on it. Then I also saw.
There's another. Yeah.
Yeah, the noise. Yeah, in the processor, is that causing accuracy issues? Yeah, definitely. So the thing is that if you measure, yeah, that completely, yeah, accuracy issues. Like you said, if you measure, like, if your quantum state is not in the correct state, if your quantum computer is not in the correct quantum state after the computation, then you're going to have like wrong measurements because you're measuring like the wrong state, and it's not in the correct state because some kind of decoherence has happened in the quantum processor or quantum chip. Yeah, there was also like a direct question, can I give some examples of how quantum computers can solve the problems of the world? This is a very high level question. So basically, I know that like one thing that people are interested in is that quantum chemistry, to predict how molecules, which are quantum systems, how they behave, how they interact. And for this, like using a quantum computer for a quantum molecule makes a lot of sense. And you could use this to design better fertilizers, to also help with like chemical processes to make like less greenhouse gases, stuff like that, optimize and kind of help with global warming. This is, for example, what Ines is pretty interested about, if you know Manish.
Yeah. Ines, she's the head of quantum innovation at IQM.
Yeah, but basically, like we still have a lot of ideas of where you could use a quantum computer. You could use a quantum computer to optimize some stuff. And if you have an optimization problem, like for example, you want to find the quickest route between some points, if you're like a delivery truck driver, then you could use like a quantum computer to optimize your route to go, to deliver your, I don't know, whatever you're delivering the quickest. Okay, there's another question, whether quantum computers can accurately estimate the value of pi. Maybe they could. I'm not sure if anybody's looking into this. I mean, you have to ask yourselves, do we need to know the value of pi even more accurately than we already do? Because I don't think so. We know already like what, millions of decimals. Why would you need even more?
Yeah, there was a recent record-breaking calculation they did. I think it was in Switzerland. It was just a week ago. And they exceeded the previous record in number of decimal places, they could estimate pi. And they used like supercomputer for like, I don't know, 100 days or something like that. Yeah. I mean, I don't know, like estimating G, gravitational constant, to like hundreds of decimal places makes sense, I guess. GPS technology, I mean, relies on how accurate you can measure that. But pi, I don't know. Maybe, I think, yeah.
Yeah. So there's, I see also another like remark about latest advancement for the quantum technology from NSW. I guess that's like New South Wales University, maybe. IQM Tech approach, is that similar to them? Yeah, so we don't have semiconductors. We have superconductors. So there are many ways of making a qubit, many systems. Some of them are going to be, have less decoherence and harder to control and read out, like what I was saying earlier, and some are going to have more decoherence and be easier to control and read out. Currently, superconducting circuits work the best, I think, but this is no reason to only focus on that, because also semiconductors, I think they haven't demonstrated a 2-qubit gate on a semiconductor. I'm not sure, but you can make qubits with semiconductors. Okay, how much powerful is quantum computer than the fastest supercomputer? Depends on the size of the quantum computer. Currently, they're slower, right? Because we only have, I think Google has like 53 qubits, and that's not a lot, If you think about if you Google how many bits your laptop has, you're going to be very much surprised. But how much more powerful is, I don't know. We'll see we're actually still waiting for a very, very concrete demonstration of a quantum computer actually being better than a classical computer. There was some work presented where this seems to be the case, but we still need to fabricate more and more qubits to have like an actual quantum advantage.
Yeah,
so,
I mean, yeah, absolutely.
So hopefully in 10 years, I'm going to give you the answer of like a quantum computer is like way faster. But it's only going to be faster for a specific set of problems. You're never going to have a quantum computer sitting on your laptop. Sitting on your desktop, because it's just too big and it doesn't make sense. Like classical computers are pretty good for classical problems, but they're very, very bad for quantum problems.
There is another researchers create scalable quantum chip that works at room temperature. So I need to click that link. Create scalable quantum chip that works at room temperature. Yeah, this is news to me. When was this article published? I don't see the date.
Yeah, it's a photonics thing.
25 August. So this is a new article. Yeah, photonics, they operate at room temperature. So that is one good thing going on for photonic guys. So this is another candidate, right, for building a quantum computer. So Miha, he knows about superconducting quantum computers. There are ion traps. There are nuclei, right, of atoms. There is photonics, right? Photonics is also sort of becoming very interesting. So yeah, there is another question for you. What is the bottleneck for photonics-based quantum computer?
Ooh, this is I actually have photonics is the kind of system that I have the least amount of knowledge on. So honestly, for photonics question, you would need to ask somebody else. For example, like I can tell you that like superconducting circuits is decoherence. For ions, it's usually the fact that you can't control ions very, very accurately. So you can basically suspend these ions in like a laser field, but you can only like control the interaction between all the ions at the same time or nothing. And this is a kind of tricky. That's the issue with that system. But for example, they have no decoherence almost with ions, but they can't control them very well. For photonics, I don't know. I'm not sure how you actually do operations on photons then.
Me neither.
Yeah, we don't know which technology is going to be the final winner yet. Like I said, currently superconducting qubits are number one because we have a 53 qubit machine from Google which runs some stuff. But yeah, things can change. If there's a breakthrough in any other field, then everybody's going to have to shift to that. That's the way it is. That's how science works. You never know what's going to happen at the end.
And yeah, it's also hard to predict, right, about the size when will, our processors double. But yeah, I mean, the trend is showing, I don't know, every 2 years.
Yeah.
Something like that, I guess, right?
Yeah, people are very optimistic.
Yeah. Yeah, there's another one. Which technology will be the final? So you answered that. But photonics base has lots of devices been developed. Yeah. I mean, there are like a lot of.
I mean, like the fundamental problem I see maybe with photonics is that if you have photon modes, photons in general do not interact with each other very much. So it's going to be very, very hard for you to make an operation with two photons that are going to kind of do some kind of interplay. I'm definitely not going to say it's impossible, but it's something that I don't know currently how it is done. Because the way that like the development of a quantum computer works is first you have to like demonstrate that you have a qubit, then you have to demonstrate that you have like more qubits, and then you have to also demonstrate that these qubits can talk to each other. If they can't do that, then you can't do quantum computation. And I honestly don't know at which point like photonics-based devices are currently.
There is another one from Papic. Can radiation cause qubits to lose quantum properties?
Yeah, qubits can lose. You can think of a qubit kind of losing a photon as kind of losing a kind of decaying to the ground state. Yeah, a qubit could also like radiate some energy from it. This does happen. Yeah. If you mean like radiation in terms like atomic decays.
Maybe cosmic radiation.
Cosmic radiation does, yeah. Cosmic radiation is actually an issue with superconducting circuits, surprisingly. There are some nice papers like that deal with this stuff, but cosmic particles hitting your like quantum processing unit, quantum chip is actually an issue.
Yeah, another question.
So this is something about superconductivity. Yeah, so superconductivity, I mean, the issue with superconductivity is what you're probably talking to is like having a room temperature superconductor. And this is where the progress is more or less like very much halted. But I mean, we can also make non-room temperature superconductor. It would make our life a lot easier if we could do them at room temperature. Yes, that is completely true. because then you don't need a huge refrigerator for your quantum chip. But we can also do them at like very, very low temperatures. It's just going to be more expensive.
Yeah, Abiskar has a comment. Trapped ions could be something in the future.
Yeah.
Yeah.
I think there are companies who are selling trapped ion quantum computers already.
They released the news yesterday, I guess. They have demonstrated or like exhibited like first 4-core quantum computer for trapped ions.
Yeah.
Yeah, that's exciting. Yeah, I would say trapped ion is second to superconducting based devices, and then maybe photonics.
In the quantum race, or maybe semiconductors are already pretty far, I think. I don't know.
Yeah, exactly. Yeah. Any more question?
Yes, I am working at IQM Germany.
Mm.
I am at the German branch, the same as Manish.
Yeah.
Hopefully, we'll also be able to visit Finland, where the HQ is soon, but COVID stuff is happening, so you never know.
Yeah.
Yeah, so I am working on basically what I was telling you about. So this is a simulations of hardware. So I'm not designing actual algorithms. I'm dealing with noise, where it comes from, how it affects the qubits, running simulations. Also hoping to how to correct for the noise, stuff like that. Ooh, sorry.
Yeah. Okay, so it's already 4:15, and yeah, we would like to thank Miha for this very exciting talk. I guess we all learned a little bit about noise, classical noise, quantum noise, and how it is ultimately detrimental, right, in quantum processes. This was a very, very nice talk. I found it very well explained, and you build it from the scratch, so that our learners, who are also at the high school level, they could grasp, I hope. Thanks, Miha, for that. Apologies, there was some annotation, and I still hope that was by accident. Maybe there was a baby, maybe somebody forgot their mouse, right? Apologies to especially Miha. And thanks everybody for joining. I see there are new joiners again. I mean, if you're joining now, it's a little late, but I think some of you are just like coming back and forth because of some connection issue, but we are concluding at the moment. And yeah, like I said, we will do more of these talks. There will be more speakers like Miha in the coming months. There will be another series like Summer of Quantum, where I have put together a list of like 5 experts in quantum who will give talks on different use cases of quantum computing, quantum computers, and I'll publish a schedule for that soon. And of course, we will also have a summit, quantum summit for Nepal in January, maybe like second week of January, where we have a cool bunch of experts again. And this will be a big one. This will be a big quantum summit. And we look forward to really catalyzing, right, a quantum ecosystem in Nepal. So we actually have one other exciting thing, which is this cocktail sessions we have at the end of sessions like this. And this is the link. Miha, you can join if you have time. If you don't have time, it's okay. We basically pair like, randomly like 2 people, and then sort of just, hang out, right? Please join this link if you are free, where I will hopefully see some of you. All right. So again, let's thank Miha. I will give a virtual clap for wonderful. I mean, clap is not virtual. It's physical, right? Sound is physical. Thanks, Miha. Yeah, and I guess this guys are looking forward to also seeing you in Nepal,
Yeah.
in the future.
Thanks for listening. Thanks for all the questions.
Yeah. All right. See you guys.